All right, today we're jumping into a really cool technique in differential equations called variation of parameters. You can think of it as the heavy-duty industrial strength tool you pull out when your usual methods they just don't cut it.
So picture this. You've got a non-homogeneous differential equation. Your go-to, the method of undetermined coefficients, is usually great, but this time it just fails. That function on the right side of the equation is a total mess. What do you do now?
And here is our villain for today's explainer. The left side, y triple prime plus y, probably looks pretty manageable. But that tan of x on the right, that's the troublemaker. And why is it a troublemaker? Because when you start taking derivatives of tan of x, they just get more and more complicated, which makes our usual method of, guessing a solution totally impossible.
And this is exactly where variation of parameters comes into the picture. It is a much more general method, and it's specifically designed to handle these really messy functions, like tan x or maybe ln x. Yeah, it's going to be more work, no doubt about it, but it gives us a reliable path to the solution every single time.
Okay, so at the very heart of this method is one single master formula. Now, I know it might look a little intimidating at first glance, but let's just treat it like a blueprint. We're going to break it down piece by piece so we can really understand how it all fits together.
First up, let's tackle the easy piece, g of x. This is simply the function that's sitting on the right-hand side of the equal sign. It's the term that makes the whole equation non-homogeneous in the first place. So for our problem, g of x is our troublemaker. Tan x. Easy enough.
Next in line is the capital W of x. This is known as the Wronskian. It's a special kind of determinant, and you build it using the fundamental solutions, we call them basis functions, from the homogeneous version of the equation. You take those functions and their derivatives and build a matrix. This thing is literally the foundation for everything else we're about to do.
Then we have its cousin, wk of x. This is what I'm calling the special Wronskian. You make it by taking that original Wronskian we just talked about and replacing one of its columns, the kth column, with a very simple column of all zeros with just a single 1 at the very bottom. And we're going to need to calculate one of these for each part of our final solution.
And boom, here is where it all comes together. This is the blueprint. See how the pieces fit? This formula gives us the derivative of the special functions we're looking for, the UKs. We find each UK prime by taking our g of x, multiplying it by the special Wronskian wk, and then dividing the whole thing by the main Wronskian w.
All right, enough theory, right? It's one thing to look at a blueprint, but it's another thing to actually build something with it. So let's put this formula into action. We're going to apply it to that tricky third-order equation we started with.
Okay, let's lock in on our mission, nice and clear. We need to find the particular solution for y triple prime plus y prime equals tan of x. We've got the tool, we've got the blueprint, now it's time to actually get our hands dirty.
So here's our game plan, broken down into 4 clear steps. First, we find the basis functions. Then, we calculate all the Wronskians we're going to need. After that, we use our blueprint to set up the integrals. And finally, we solve those integrals to get our answer. Let's do this.
Step 1. The first thing we got to do is kind of pretend that tangent of x isn't even there for a second. We just solved the simpler, homogeneous version, y triple prime plus y prime equals 0. When you do that, the solutions turn out to be 1, cos x, and sin x. These are our fundamental building blocks.
And now we can use those building blocks to construct our main Wronskian. Just look at the structure here. The top row is just the functions themselves, 1, cosine x and sin x. The second row? That's their first derivatives. And the third row, you guessed it, their second derivatives. The next step, of course, would be to actually calculate the determinant of this 3×3 matrix.
So now you can see the whole machine starting to turn. We'd calculate our main Wronskian, w, and then the 3 special ones. Then we just plug all those pieces into our master formula. This gives us 3 different expressions for u1 prime, u2 prime, and u3 prime. The final step, and let's be honest, often the hardest one, is to integrate each of these to find the pieces of our solution.
So this method is a powerhouse. It's incredibly powerful, and what's great is that it always works. But, and there's always a but, right? With great power comes a pretty hefty price tag. So let's go ahead and open up the user's manual and read the fine print.
Which leads to the obvious question, doesn't it? If you have this super tool that can solve pretty much any problem you throw at it, why on earth would you ever use a simpler one? There's got to be a catch. And here is that catch. There are two big ones. First, calculating the determinant of a 3x3, or heaven forbid, a 4x4 matrix of functions can be incredibly tedious and super prone to little mistakes. And second, and this is the real kicker, even after you do all that algebra, the final integral you set up might be really, really hard, or maybe even impossible to solve with standard techniques.
And that brings us to the golden rule, the main takeaway here. If the method of undetermined coefficients is an option, meaning your g of x is a nice polynomial or an exponential or a sine or a cosine, you should always use it. It's just so much faster and simpler. You want to save variation of parameters for the moments when you have absolutely no other choice.
And that leaves us with one final thought to chew on. Knowing how a formula works is one thing, but really mastering a topic comes from understanding its limits. So how does knowing the weaknesses of a tool actually make you a smarter, better problem solver? We'll leave you with that. Thanks for tuning in.